what are we doing? I can use problem solving to find the next term in a pattern. How are we going to do this? So we're going to find the pattern, and then we're going to use it to figure out the next term in the sequence. And one of the reasons why we're doing this is because pattern recognition is super duper important for us. We're going to see lots and lots and lots and lots of patterns, and if we can't find a pattern, we can't do a problem. You know, if we can't see how the process that we do is the same each time, then it's going to make our lives miserable. So you have to be able to find a pattern. So let's start off with a pattern like this. And so what we need to be able to do is we need to be able to figure out what's going on from one number to the next number, right? We're going from 3 to 9 to 27 to 81. What are we doing from one number to the next? What's happening? Can anybody tell me? Yeah, you're just multiplying by 3, right? So going from one to the next, it's just multiplying by 3. So if I wanted to find the next one, I would have to multiply by 3 to get that one too, right? This is kind of like when we were finding the other endpoint, right? We know from one thing to the next, we times 3, so going to the next one, we times 3. So the next one would be like what, like 243, right? And the one after that, ain't nobody got time to do that in their head. 3 times 3 is 9. 3 times 4 is 12. 3 times 2 is 6 plus 1 is 7, right? So here's the first term that they wanted. Here's the second term that they wanted. If you look, it said, what are the next two terms in each sequence? So make sure that you read the directions. Make sure that you read the directions here. All right, good job. Give this one a try. So this one is not a numerical pattern, right? This is a visual a visual pattern. So if I want to find the next two terms in each sequence, I should be able to describe them, right? So I'm not asking y'all to be able to, because you can't draw in the chat, but I'll put a little bit of a description as to what we're looking at for the next two terms. Okay, so let's look. We've got a triangle, so that's what? That's 3 sides, right? And here, this is a square that's inscribed in this triangle that has 4 sides. 5 sides, we call that a pentagon. So if it's 3 sides, 4 sides, 5 sides, what's going to be the next one? You're going to have to excuse my heinous drawing skills here. It's going to be a hexagon. And again, don't mind my terrible drawing skills. And then the next one will be a heptagon. 7 sides. So let's see how ugly this is going to look. We're going to try our best here. There we go. That terrible looking heptagon. But that's okay. But that's the idea, right? We're finding what the pattern is. You can always break each pattern down into something very easy to figure out. And that's all we're talking about here. All right, now take a look here. Look at the circles. What conjecture can you make about the number of regions that 20 diameters form? So first of all, there's a word in here, conjecture. And conjecture, all that means is an educated guess. And in the case of what we're doing, so think about, like, for those of you who have taken a science class, the word conjecture carries the same weight as the word hypothesis. And a hypothesis is just like, it's in science, it's an educated guess, right? So anytime you think conjecture, you can just change that word to hypothesis if you like that better. I personally do. So we want to know the number of regions. So if we look here, how many regions are cut? We've got one diameter, two regions, right? We've got two diameters now, one going top to bottom, one going left to right. We count, now there's four regions. If there's three diameters, you have six regions. So look at the way, like, the diameters cause the number of regions. 1 to 2, 2 to 4, 3 to 6. Going and looking at sort of the cause, right? We don't necessarily care about the horizontal pattern so much as the vertical pattern, right? So diameter to region, we're talking about times 2, right? So for every diameter, and I can write it out as a formula, right? 2 times the number of diameters equals the number of regions, right? Take the number of take the number of diameters times 2, you get the number of regions. Take the number of diameters times 2, you get the number of regions. Take the number of diameters times 2, you get the number of regions. So now we found our pattern. We have made a conjecture. We have shown that it works. So now let's answer this question. The number of regions that 20 diameters makes. Well, look, here we've got our pattern. So let's plug it in. 2 times the number of diameters. So what we're saying is, because we only have the first three terms, we don't necessarily know that it's true. But based on what we have, and this is, why we're talking in terms of hypotheses and conjectures, because we're saying based on the information we have, if the pattern holds, then what we could say is that if we get up to 20 diameters, we better have 40 regions. Y'all get what I'm saying? All right, so let's try one more. Again, we're going to figure out the pattern. I'm going to leave this to you. Okay, so again, what we want to be able to do is we want to be able to figure out how we can find term number 21 from what we have here. And I don't want to have to go through and write them all out. I don't want to have to write out all the way to the 21st term. But what I can notice is that this pattern repeats every 3 times, right? 1, 2, 3, 4, 5, 6. So 1, 4, every plus 3 gives you the same thing, right? Every plus 3 gives you the same thing. Every plus 3 gives you the same thing. So how does that help us with our 21st term? Well, wait a minute, hold on. 21 is also a multiple of 3, right? So if this is repeating every 3, well, wait a minute, hold on. I can do something with that. Because look, if it's repeating every 3, the ones that are multiples of 3 are always going to be the same, right? Multiple of 3, multiple of 3. So like, if I keep going in this pattern, I'm eventually going to hit number 21 on B, right? So the answer has to be B. Likewise, if I did the 25th, I could say, wait a minute, okay, so that's, if I divide by 3, that's not going to come even. That's going to be a remainder 1, right? Right? It's not going to come out even. It's going to come out with a extra little plus 1 there, right? To say it another way, if I look at 25 and I divide it by 3, that goes in 8 times. Remainder 1, right? So we want to know what numbers on here when you divide by 3 give you remainder 1. Well, that's 1, 4, 7, and so on. So for that one, if you're looking at the 25th term, you're talking about, well, what's the red one, right? I keep thinking red, white, and blue here, so I don't know if that's what they mean, but that's I keep. You can do that for any number. Like, let's look at the number like 731. Well, okay, let me divide by 3 and see what the remainder is. 3 goes into 7 twice. 7 minus 6 is 1, drop down to 13. 3 goes into 13 4 times. And I don't care about this number up here. I care about the remainder, right? Once, drop down the 1, goes into 11 3 times, 3, 6, 9. So the remainder here is 2. What numbers here are going to have remainder 2? Well, that's 2, 5, 8, and so on. So if I want the 731st term, we're going to have a W. That's what they're trying to do here. And this is actually a really cool thing. When I was taking a class over the summer, we talked about what are called residue classes of numbers, and that's exactly what you do. You take a number, you take a number, and it's like, okay, well, if I'm using this number, what's the remainder of every single number when I divide by the number I pick, right? And so it basically takes all the numbers and splits them up into categories, which is really cool. And so that's what's really happening here is that, okay, yeah, sure, RWB, RWB, but really what you can think about is you're taking all the numbers and you're splitting them up into 3 classes. The class is remainder 1, the class is remainder 2, and the class is remainder 3. That's just really neat. Or remainder 0, I guess, not remainder 3, right? Because it divides evenly, no remainder. Okay, now here's more conjecture-y stuff, right? So what conjecture could you make about the sum of the first 30 even numbers? Once again, when they're asking about making a conjecture, they're really wanting you to put together a formula almost. So like what happens when we're adding up the first one even number? Well, that's just 2, right? And we want to get this into something based on 1. Here we want to get something based on 2. Here we want to get something based on 3. And we can do this as many times as we want until we can figure out what the pattern is, right? So let's figure out what that is. So one even number, we got 2. 2 even numbers, we've got 6, 12, 20, right? And so I always like to get things in terms of, if I want to find a formula, okay, so let's get things in terms of 1, right? Here's like my X, here's my Y, here's my input. I want an output. 1, well, I could do like 1 plus 1. That might work. Let's see. 2, 6 is 2 plus 4. This isn't helping me much, right? 4. Oh, well, there you could come up with something with that, but what I'm thinking of is harder than what maybe they want. So let's try something else. That's so let's maybe try multiplication. Let's see if we can't find something more consistent here. So 2, well, that's 1 times what is 2? 2. 2 times what is 6? Let's figure out with 12. 3 times what is 12? 4 times what is 20? And now, if you look, 1 times 2, 2 times 3, 3 times 4, 4 times 5. So what this really is, this is x times 1 more than x. The number times the number after it, right? If x is 1, x plus 1 is 2. If x is 2, x plus 1 is 3. If x is 3, x plus 1 is 4. If x is 4, x plus 1 is 5. Same idea. So try this one on your own. Same idea, right? What conjecture could you make about the sum of the first 30 odd numbers? So we did even number, we added up all the even numbers. Now let's try adding up all the odd numbers. All right, so let's go over this. Once again, I'm going to do the same thing. I'm going to make myself a little chart just so I can look. So if I look here, first one odd number is just 1. First 2, first 3, first 4, first 5. Right? Well, so what do these add up to? 1, 4, 9, 16, 25. So look, if I want to figure out 1 times what is 1, 2 times what is 4, 3 times what is 9, 4 times what is 16, 5 times what is 25. Well, hey, this looks like a really cool pattern. It looks like if it multiplied by itself, right? So, if this is your x and this is your y, that means that if you want to find the first x odd numbers, just square it. If you want to find the sum of the first 2 odd numbers, square 2. The sum of the first 3 odd numbers, you can square 3, and so on. If you want to find the first 50 odd numbers, just square 50 and it'll add up. And that's what it would be. That's really cool. We can find these patterns and we can say, wow, these are things that I can do. These are things I can discover. Look for patterns. Okay. So this one is about reading a graph, and so first things first, when you have some dots and they're going to be asking you, okay, so what happens after? If you look, like if I draw a line in here, it's not going to be perfect because it's never going to be exactly perfect. But like if you look, it does pretty well going down 500 each time, right? So if I wanted to come up with a possible conjecture about what's happening, they're saying in May. Well, where's May? May is right here, right? November, December, January, February, March, April, May. Well, where's May? If we're following the trend, May should be, roughly speaking, here at 800. Right? And this is literally just putting your finger down right here and then going up till you hit the line and then going over to the left to find what number corresponds, right? So what comes next? Same picture. Now they're talking about June. If you had to guess, and I want y'all to put it in the chat, if you had to guess, what would you think the answer is going to be for the number of backpacks in June that they can sell? And once again, if you go through and you try and line it up with the dots the best you can to get as close as possible, we can tell that it's going down roughly 500 per. So it was 850 in April, should be about 8,500, should be about 8,500 in April, should be about 8,000 in May. So going down 500 again should give us 7,500, right? And I know this is 0, but this is basically like a break in the graph. This is bad graph making. Textbook, you should know better. They use a break in the graph a lot to sort of make it look like things are closer than they should be. Like you're looking at, oh wow, this is dropping down 500 each month. That looks like a lot. See how far down the graph it's going? But no, it's not, right? And a backpack company should be expecting that. I don't know why they're seeing such a high amount of backpacks in November, to be honest. What it should be, really, if you think about it, there should be a ton of backpacks in like July, August-ish that they sell, and then maybe nothing. Oh, you know what this probably is? Why we see such a high uh, purchasing of backpacks in November is that's probably like a secondary bump. A bunch of kids broke their backpacks and now they need to buy a new one. So like I would imagine like July or August would be the peak. And then September, October, November, well, September, October goes down and then spikes back up in November apparently. And then it goes back down again until July or August or something like that, which I think is that makes sense, right? I'm not saying that this is part of the problem, but no, we're just thinking aloud and talking about how we could rationalize the way that this looks. Okay, let's look at another problem. Counterexample. So, okay, so we talked about a hypothesis, right? Conjecture sort of means hypothesis. And if we have a hypothesis, in order to give it validation and um, make it into a theory, right? We talk about that in science. We test it. Well, you're going to do the same thing for a conjecture. That's what we were talking about earlier. We made our conjecture and it held for what we could write down, so it made sense to have it, right? But here, what we can do is we can find a counterexample and say, hey, this doesn't work because this situation breaks our pattern. So the conjecture that they came up with is that if the name of a month starts with the letter J, it must be a summer month. And you're thinking June, July. Yeah, right? But who can tell me what month starts with the letter J but is not a summer month? Yeah, that's exactly right. So since January is not summer, we know that this conjecture doesn't hold. We're going to talk about more articulate ways to talk about this next week and the week after. But basically, we're saying, okay, well, if it starts with a J, then it's a summer month. But now we're saying, wait a minute, hold on. But January is not a summer month. So this statement must not be right all the time. So it's useless. One of the things in math is we don't like it when things are only right some of the time. We don't want them to only be right some of the time. If we're going to make a statement about something, it had better be right all the time. Y'all have talked about always, sometimes, never type stuff. We don't want sometimes. We either want always or never, because those are the things that can help us. Those are the things that can be interesting. Sometimes don't work. So look, here's another one. When you multiply a number by 2, then the product is greater than the original number. Who can come up with a number that if I multiply it by 2, it's not bigger anymore? So look, if I do 1 times 2, is 1 getting bigger? Yeah. I want this number to not be bigger anymore. So this would reinforce my conjecture, right? This would tell me my conjecture is right. So But the second one you're saying is a good one. Look, 0 times 2. When I multiply 0 by 2, does it get bigger? No. Here's another one that's a really good one, like negative anything. Let's say negative 5. Negative 5, if I multiply that by 2, does that get bigger? Is negative 10 bigger than negative 5? No. It's more negative, so it's smaller, right? So these two here are examples of ways that you can show, hey, it doesn't work. Here, it stays the same. That's not greater than. Here, it gets smaller. That's definitely not greater than, yeah? So that's what we're talking about.